Now we are examining the power in frequency domain, and in the final frame, which is this frame, we will be seeing some of the application of power calculation in frequency domain. So let's see it now. There are going to be 3 examples that we are going to examine. One of them is the compensation. The other one is the line efficiency. This is the electrical power is produced in one place but consumed in somewhere else. So to carry the electric power from that origin to the consumption side, there is going to be some loss, power loss in between. So that power loss is lost. So we're going to calculate this loss. This loss affects the efficiency of using the electrical power. So the third application that we're going to see is the maximum power transfer. So we have seen the similar maximum power transfer in introduction to electric circuits. In this we said Thevenin equivalent resistance value must be the load resistance value in order to transfer the maximum power to the load. So in this case, in frequency domain, this resistance value is going to be the impedance relation. So we're going to see that one as well. So let's move to open circuit, open board, to see step by step the compensation. Open board, and then move this up. Here you are. This left hand side circuit here represent an electric motor. This is an electric motor. You see, electric motor has got some coils in it. Coil is inductors in it. So this inductor has a resistor value. Since this is the copper wire from which the coil made up, this copper wire is resistor value is very low because the copper is a conductor. So in this case, you see that resistor value is very low. It is 3 ohm, and the inductor value is this. So that represents now this electric motor here. This is the source. So we are getting the electrical motor to run something. We are getting the electrical power from the system and then run the motor to transfer it to some other energies. All the motor included appliances can be considered in this group. For example, in our houses we've got refrigerator, has got an electric motor in it, and washing machine has got an electrical motor in it, and most of the manufacturers, they use the electrical motors. So this electrical motor consume some power. So we are going to calculate that power. That power is going to be the average power, P average. We are going to calculate this. And then we are going to calculate the reactive power as well. So we know the average power is 1/2 Vm. Vm is the maximum value, Im is the maximum value of the current, cos theta V minus theta I. So this is the phase difference between voltage and current. So phase difference between and voltage and current, what we mean is this is our motor. So the voltage here, this voltage angle is that theta V. And the current consumed by the motor, this current angle is that theta I. So the phase difference between those two, voltage and current, which is the voltage and current of this motor, should be what? So in our calculation, we are going to say it is going to be different from 0. Since this is different from 0, cos theta phi is going to get a value. So we are not going to get the maximum average power. So how we are going to arrange that? So how we are going to arrange it as we are going to calculate this, and then we are going to calculate Q, which is the reactive power, is equal 1 over Vm Im sin theta v minus theta I. Let's do this calculation now. So if you consider now theta v minus theta e is the angle of this impedance. I'll show it to you now. That is Vs. Let's consider that Vs as a phasor. V over I is equal to the impedance, isn't it? That is Z. What is this Z? Is the serial connection of those two elements. So it is 3 plus J omega L. So 3 plus J, that omega is that omega, isn't it? So that is omega. So that is 100. L is 40 millihenry. Since it is milli, 10 to the power minus 3. That is L. And omega was 100. I put 1. So we already put that 100 here. Okay. So if we do this calculation here, so 3 zeros here, that's minus 3. So it's going to be 3J4. That's the impedance. Now this impedance is also Vm power. Let me write it. Okay, let me write this impedance now in polar coordinate. What is going to be the module of it? Module is the square of this, which is 9, square of this, which is 16. 9 plus 16 gives you 25. Square root of 25 gives you 5. So the module of this impedance is 5. E to the power J arc tangent 4 over 3, isn't it? So that is the angle. Now I am saying this angle is this angle. Why is that? So this impedance is Vm e to the power j theta v. That is the angle of the voltage, isn't it? So this one, Im, is the maximum value of the current, which is this current, e to the power j theta e. Theta e is the angle of the current, isn't it? So this means Vm over Im e to the power j theta v minus theta e, isn't it? If you move that up. So theta v minus theta e is that angle here. So if you do this calculation, you're going to end up with this 1 point something. Get the arctangent of it. You're going to get theta v minus theta e is 53 degree. If you find the cos phi, cos theta v minus theta e for 53 angle, it's going to be 0.6. So what is left is now calculation of P average. P average is 1 over 2. Vm here is that, isn't it? Because the source maximum voltage value is also the same as this element voltage maximum value. So 310 is that Vm. What is Im? So you could see it here. Im is, we know the module of Z, which is this Z module, isn't it? So Vm over Im, module of Im, is equal 5. So this is going to be 310 over 5, isn't it? So I am saying if you move that 5 here, Im here, Im is going to be equal Vm over 5. So Vm was already 310, so 5 multiplied 0.6. After that calculation, what you're going to have is 5,766 watts. That is average power. If you do the calculation for the reactive power, these are going to be the same, but this is going to be sin 53 degree. If you do this calculation, you're going to end up with 7,665 VAR. So what happened is there now. Interpretation of this analysis tells us that is the useful power. But we are taking that amount of current from the circuit. This current determines this reactive power. So energy supplier companies says that I am going to charge you for this power as well. Not the useful power only, but the other reactive power as well, he says. So, but they do not apply this rule for the houses, because in the houses, number of electrical motors are very limited. Washing machine and isn't it washing machine and what refrigerator, for example, has got the motor in it. So these are limited. The other electrical appliances do not have the electrical motor. It's a few of them, exceptions of course. So they don't charge for this reactive power that we consume in our houses, but they do charge for the manufacturers. Why is that? Because they use many electrical motors. You see, any energy that you require, you get this energy from the electrical motor, electrical energy, and then transfer it to other energies in the manufacturing area. So the energy supplier, electrical energy supplier, they do charge for the reactive power as well. But what they do advise is this. They say, so you can steal less money by doing a change in your circuit, that means in your electrical motors, in order to make that reactive power equal to 0. If this reactive power is equal to 0, I'm not going to charge for that. So our aim is now how we can get that amount of power for our motor, and how we can get, at the same time, how we can get rid of this reactive power. So the solution is to apply a capacitor in parallel to our electrical motor. So we are going to see now our next step is a synthesis problem. The question is, what should be the capacitor capacitance value that I'm going to connect here in order to make this reactive power equal to 0 while keeping this power as it is. Now I am saying this power in this circuit, the useful power is going to be the same for this motor part here in this circuit and this. Why is that? Because I am saying the voltage here for this motor is the same as this, isn't it? Because this is in parallel. That means this voltage, this load, this motor voltage is the same as this capacitor voltage. Also, this is the same as the source voltage. So, voltage does not change. I am saying the current that we consume here is not going to change whether you are in this circuit and this circuit. Why is that? Because this power divided by this impedance gives you that current, isn't it? It is also true for this one, because we already said that this power is the same as this element power. So if I divide this equivalent circuit impedance value, that voltage, I'm going to get the same current here and the same current here. So if the voltage and current of this motor is not changing whether you are in this circuit and this circuit, so that means you're going to get the same average power. So what is going to change is this reactive power is going to change. We're going to make this 0. And what is also will be changing is that current here. This is going to be a new load after we put that capacitor in. So we are going to deal with this load now. So if you look at this load, this capacitor, we know that capacitors do not consume any energy. We already find the average power of a capacitor is equal to 0. So this is not going to change my average power. But this will be changing this Q reactive power. When this is changed, that means this current is going to change. So this impedance current, not this one, for example, as you see here. So this ZL new impedance current will be changing, will be different from this one. Okay. So let's do this calculation now. So the synthesis problem is what should be this capacitance value in order to make this reactive power equal to 0. Let's do it now. What is this ZL? ZL is the parallel connection of this impedance and this, isn't it? So this impedance we already calculated here is 3 plus 4 G in parallel with 1 over J omega C. That is impedance of a capacitor. So this is this, and this capacitor impedance is this. So multiplication of these impedances over the summation of these impedances is going to be my new equivalent impedance. 3.4 C times 1 over omega C, J omega C, over 3, 4J plus 1 over J omega C. If you do this calculation, you end up with ZL. I will be writing from here, and I will tell you how you're going to find that. 3 plus 4J over 1 minus 4 omega C plus 3 omega Cj. So what you're going to do is very simple. You're going to multiply this numerator and denominator with J omega C. If you do this multiplication, this becomes 1. So numerator is going to be 3 plus 4C. So we're going to multiply this denominator by J omega C. So it's going to be 1 here, and this one is going to be multiplied with J omega C. You end up with this. So if you look at now this, so this is ZL is equal what? Is equal that voltage over current, isn't it? So that voltage, make it a different color. That voltage here is that source voltage, because this impedance voltage is this source voltage, isn't it? This current here is this current. So if you divide this voltage to this current, you're going to get that impedance, that's that impedance. So this impedance, let's make it in red afterwards. So it's going to be angle of that, so you can consider it. So this is, what is this model of this is 5 e to the power j, we already done it, arc tangent 4/3. It's not good, isn't it? So we'll make it a bit better. J arc tangent 4/3 and divide by. So the model of this element, I'm going to write this model as like. I do not need that. I'm going to show it to you. So this imaginary part is going to be divided to this one. So arc tangent e to the power, sorry. So we are writing in polar coordinate, e to the power j arc tangent 3 omega c over 1 minus 4 omega c. So this is now theta v, that is theta e. So what I am expecting, theta v must be equal to 0. So if theta v is equal to theta e, that means that angle is 0, isn't it? The difference is 0. Sine 0 is 0. So my reactive power is going to be 0. So that means that theta v must be equal to this one. So theta v, so I made a mistake. Theta v is this without r, altogether theta v. So this is going to be this, isn't it? So tangent, arc tangent, arc tangent. So 4/3 must be equal 3 omega c over 1 minus 4 omega c, isn't it? These two should be equal. This ratio, if this ratio equal to this one, arc tangent result angle is going to be the same as this angle. So if you do this calculation, what is omega here? Omega is the same, isn't it? So that's the omega. So sorry, that is the omega 100. So if you put that omega 100, then you can calculate that C here, that you're going to end up with 1600 microfarad. So this is the capacitor value we found. We can easily say that since this angle is this angle, is the same as this angle, so my reactive power is going to be 0, and my average power is going to be the maximum value, because theta v minus theta e is 0, means cos theta v minus theta e is equal to 1, so that's the maximum value. Now I am saying this maximum value, while this is in maximum value, this calculation, the average power is not going to change, as I already said. What is going to change is that current here. So the maximum value of the current will be changing. So if you do this calculation now, so I know that Q is equal to 0, reactive power is equal to 0, P is going to be the same as this, 5,766 watt. So what is this current now? Here, so this is the current, the maximum value current is this. So after you put that omega here, omega equal to 100, that's your microfarad, you're going to find this current, maximum value of this current, which is this, isn't it? So that is maximum power, maximum current here. Let me write it here. So IM is square root of 1/4 omega c square plus 9 omega square c square. So I am saying this maximum current value here is going to be this one. But this I1 here is going to be the same as this I1. So that means the electrical energy that I get from the supplier is determined by this current. Now this current has been reduced. If you calculate the current here, you're going to get a high current. But after the compensation, you're going to get a less current here. What is this current? The maximum value of this current. Is this, isn't it? That is the maximum value. So that is I maximum current here. And that I is this. If you do the calculation, you're going to see it is going to be less than this. So let's interpret the conclusion now. I put in parallel a capacitor to my motor and end up with no change in average power. So I will be paying the same money. I will be paying for this electrical power to the supplier. After the compensation, since my reactive power is 0, I will be paying for this average power only. So that means I will be paying less money to the electrical supplier. On the other hand, electrical supplier firm is going to give me less electrical power since I reduced that current. Since this current is reduced, means this voltage hasn't changed. That means you could use the diameter of the copper wire less. So that means supplier investment has been reduced. So this is an environmental solution at the same time. Why is that? Because I will be consuming less amount of energy in order to run my motor. So this is good for the environment, isn't it? You are using less energy to do your job. That's why a beneficial solution that we found. So that's end of this video then. Let me stop it then.